Praise be to Allah, the cherisher and sustainer of the worlds. I'm Dr. Ramsha Mushtaq Khan, and today I take this opportunity to discuss the topic analysis of variance, also called as ANOVA, under the kind supervision of Professor Dr. Saira Afzal. Quote of the day. Ego is inversely proportional to knowledge. More the knowledge, lesser the ego. Lesser the knowledge, more the ego. Albert Einstein. The content outline of today's presentation is one-way analysis of variance, introduction to F statistics, the sheaves and the Tucky test, and two-way analysis of variance. At the end of this presentation, the participants will be able to understand and apply the one-way ANOVA technique to determine if there is a significant difference among three or more means, determine which means differ using the sheaves or the Tucky test when null hypothesis is rejected in the ANOVA, use the two-way ANOVA technique to determine if there is a significant difference in the main effects of variables or in their interaction, and recognize the recent advances in this context. ANOVA is an analysis tool used in statistics that splits and observes variability found in a data set into two parts. One is the systematic factors and two is the random factors. Systematic or fixed factors are the ones that have a statistical influence on a given data set, and random factors do not have a statistical influence on a given data set. ANOVA is also called the Fisher analysis of variance. It is the extension of T and the Z test and is used to compare two variances. ANOVA is used in regression studies for three or more group means to determine whether there is a difference between them, which is the one-way ANOVA, and to know the influence that independent variables have on the dependent variables and the interaction effects of two variables, which is also called as two-way ANOVA. When an F test is used to treat a hypothesis concerning the means of three or more populations, the technique is called analysis of variance, commonly abbreviated as ANOVA. Although the t-test is used to compare two means, it should not be used to compare three or more means. ANOVA uses F-test to statistically test the equality of means to determine whether the variability between group means is larger than the variability of the observations within the groups. If this ratio is sufficiently large, it is concluded that all the means are not equal. For three groups, the F-test can only show whether or not a difference exists among the three means, not where the difference lies. The statistical tests, the sheaves test and the Tucky test are used to find where the difference exists. Understanding the basics, the F statistic is basically a simple ratio of two variances. Variance is a measure of dispersion or how far the data is scattered from the mean. Larger values represent greater dispersion, and variance is the square of the standard deviation. This is the formula of variance for population and sample, and the standard deviation for population and sample. The population variance is denoted by sigma squared, summation xi minus mu whole square divided by capital N, where sigma square is the population variance, xi is value of the ith element, mu is the population mean, and capital N is the population size. Assumptions for the F-test. The following assumptions apply when using the F-test to compare three or more means. Number one is the populations from which the samples are obtained must be normally or approximately normally distributed. The samples must be independent of each other, and the variances of the populations must be equal. In the F-test, two different estimates of population variance are made. The first estimate is called the between group variance. It involves finding the variance of the means between groups. And the second estimate is the within group variance, which is made by computing the variance using all the data and is not affected by differences in the means. This diagram shows the mean for three groups. Mean 1, mean 2, and mean 3 is depicted in the figure, and two estimates of population variance. Number 1, the between group variance, and number 2, within group variance is shown. Also, the total variance and the concept of grand mean is displayed. Testing the hypothesis using the F test. If there is no difference in the means, the between group variance will be approximately equal to the within group variance, and the F test value will be close to 1. So we will accept the null hypothesis. When the means differ significantly, the between group variance will be much larger than the within group variance, and the F test will be significantly greater than 1, and we will ultimately reject the null hypothesis. The between group variance is sometimes called the mean square B, MSB. The numerator of the formula to compute MSB is called the sum of squares between group, SSB. The within group variance is sometimes called the mean square W, MSW, and the numerator of the formula to compute MSW is called the sum of squares within groups, SSW. This is the F test formula where F is equal to between group variance divided by within group variance, and mean square between groups and divided by mean square within groups. The F statistics is based on the ratio of mean squares. The term mean squares is simply an estimate of the population variance that accounts for the degrees of freedom used to calculate that estimate. This is the summary table of ANOVA. Here the source is the estimate between groups and within groups. The sum of squares is denoted by SSB and SSW. The degree of freedom, I will discuss about it later on. Between groups, it is calculated by K minus 1, and within groups, it is calculated by N minus K. The mean squares is denoted by MSB and MSW, and F is obtained by dividing MSB divided by MSW. In one way, ANOVA output, the adjusted mean square is used, which is the sum of the standard deviation, squared deviations divided by the factor degree of freedom. One point to remember is that further apart the group means are, the larger this number becomes. Also, an estimate of the variability within each sample is required. To calculate this variance, we need to calculate how far each observation is from its group mean for all observations. So technically, it is the sum of the squared deviations of each observation from its group mean divided by the error degree of freedom. The F statistics incorporate both measures of variability as discussed. To consider how these measures can work together to produce low and high F values, let's assume graphs to compare the width of the spread of the group means to the width of the spread within each group. This is the F plot depicting low F value. Three groups with three means are shown, and in comparison, this is a F plot depicting high F value. The low F value graph shows a case where the group means are close together, having low variability relative to the variability within each group, and the high F value graph shows a case where the variability of group means is large, high variability relative to the within group variability. In order to reject the null hypothesis that the group means are equal, a high F value is needed. But how to know that if the F value is high enough? A single F value is hard to interpret on its own. So in order to place the F value into a larger context before interpretation, the F distribution is used to calculate probabilities. Now, F distributions and hypothesis testing. For one-way ANOVA, the ratio of the between group variability to the within group variability follows an F distribution when the null hypothesis is true. When a one-way ANOVA is performed for a single study, a single F value is obtained. However, if multiple random samples of the same size from the same population are drawn and the same one-way ANOVA is performed, many F values are obtained, such that a distribution of all of them could be plotted, and this type of distribution is called a sampling distribution. Since the F distribution assumes that the null hypothesis is true, the F value from any data can be placed in the F distribution to determine how consistent the results are with the null hypothesis and to calculate the probabilities. The probability that is to be calculated is the probability of observing an F statistic that is at least as high as the value that a study yields. This probability allows determining how common or rare the F value is under the assumption that the null hypothesis is true. If the probability is low enough, it is concluded that the data is inconsistent with the null hypothesis and the evidence in the sample data is strong enough to reject the null hypothesis for the entire population. This probability is also known as the p-value. After an F is computed, the probability value can be computed from an F table. To use this table, we need to know two degrees of freedom. First is the degree of freedom for numerator, which is equal to k minus 1. And second is the degree of freedom for denominator, which is equal to n minus k, where k is the number of groups and n is the total number of subjects in all groups. The parameter degree of freedom for the denominator is often called degree of freedom error or DFE. Now let us consider this example in which a researcher wishes to try 3 different techniques to lower the blood pressure of individuals diagnosed with high blood pressure. The subjects are randomly assigned to 3 groups. The first group takes medication, the second group exercises, and the third group follows a special diet. After 4 weeks, the reduction in each person's blood pressure is recorded. At alpha equal to 0.05, test the claim that there is no difference among the means. So this is the 3 groups. The first group is taking medication, second is exercising, and third is taking a special diet. First, we state the null hypothesis and identify the claim. The null hypothesis states that the means for all 3 groups is equal. And the alternative hypothesis states that at least one mean is different from the others. So in step 2, we will find the critical value. Since the total number of groups, which is k, is equal to 3, and total number of subjects in each group, which is n, is equal to 15, and alpha is known, which is 0.05. We will find the degree of freedom for the numerator and the denominator and obtain the critical value, which is obtained from the table H. It comes out to be 3.89. In step 3, we will compute the test value, find the mean and variance of each sample. And ultimately, we will find the grad mean, the mean of all values in the sample. Then we will find the between group variance by the formula. Then we will find the within group variance by the formula. And ultimately, we will compute the F value. Then we will make the decision to either to reject or accept the null hypothesis. In this case, the null hypothesis is rejected because the F value comes out to be 9.17, which is far greater than the critical value 3.89. And in step 5, we will summarize the results that there is enough evidence to reject the claim and conclude that at least one mean is different from the others. Now coming to the post hoc analysis, the sheaves and the Tuckey test. When the null hypothesis is rejected using the F test, the researcher may want to know where the difference among the mean is. The sheaf test and the Tuckey test are procedures to determine where the significant differences in the means lie after the ANOVA procedure has been performed and help to control type 1 errors. The sheaf test, in order to conduct the sheaf test, one must compare the means 2 at a time using all possible combinations of means. For example, if there are 3 means, the following comparisons must be done: x bar 1 versus x bar 2, x bar 1 versus x bar 3, x bar 2 versus x bar 3. This is the formula for the sheaf test, where xi and xj are the means of the samples being compared, ni and nj are the respective sample sizes, and the within group variance is denoted by SW. To find the critical value F bar for the sheaf test, multiply the critical value for the F test by k minus 1, as is shown in this equation. And there is a significant difference between the 2 means being compared when Fs is greater than the F bar. The Tuckey test can also be used after the analysis of variance has been completed to make pairwise comparisons between means when the groups have the same sample size. The symbol for the test value in the Tuckey test is Q. This is the formula for the Tuckey test, where xi bar and xj bar are the means of the samples being compared, and n is the size of the sample, and the within group variance is denoted by SW square. ANOVA is the analysis which is employed to test the effects of 2 independent variables or their effects on one independent variable. In addition, the interaction effect of two variables can be tested. Variables or factors are changed between two levels, that is, two different treatments. The groups for a two-way ANOVA are also called treatment groups. A two-way ANOVA has several hypotheses. There is one for each independent variable and one for the interaction. This is the summary table for two-way ANOVA. Here the source estimates A into B, and within the group error. The sum of the squares is denoted by SSA, SSB, SSA into B, and SSW. The degree of freedom is denoted by A minus 1, B minus 1, A minus 1 into B minus 1, and AB into N minus 1. And similarly, the value of S is calculated by dividing the mean squares. The assumptions for the two-way ANOVA are the same as that for the one-way ANOVA. Only the difference is there is one addition of the two groups must be equal in the sample size. Recent updates. The heteroscedastic two-way ANOVA under constraints. In this article, two simple tests for two-way ANOVA under unequal variances requiring some constraints which cannot be solved by classical regression formulas is derived. It is done by taking generalized p-value approach and provide explicit formulas to handle the constraints. The first test is an extension of the fiducial one-way ANOVA test, which tends to assure the intended size of the test, but tends to be conservative. And the second test reduces that drawback, but may slightly exceed the intended side of the test. The second test is also a generalized test that is numerically equivalent to the parametric bootstrap PB test, which contains some unintended glitches in formulas, which will be rectified. Moreover, in this approach, does not require good estimators of parameters as the PB approach does. So in this approach, they will use the analysis of lifetime data in engineering and analysis of survival data in studies of the public health. By taking similar approach, researchers are also encouraged to derive generalized tests in other ANOVA applications such as higher-way ANOVA, ANCOVA, and ANOVA under heteroscedasticity, especially in mixed effects model applications such as repeated Meyers, RM ANOVA, where the PB approach run into difficulties. Two common mistakes in applying ANOVA test guide for the biological researchers. This article states the importance of statistics in biological research. The evidences from literature points the persistent statistical errors, selection of non-proper statistical tests with the consequence of misinterpretation of the scientific results which are published in international journals. One of the most extensively used statistical tests in the field of biology, preclinical and clinical, is analysis of variance, which is ANOVA. ANOVA test is in place of multiple t-tests to compare the means of more than two groups at a time, and hence there are some important points which biologists should be aware of to avoid misinterpretation of results with the consequence of wrong conclusion. The first mistake is identified as using the classic ANOVA or the Wilks ANOVA test, and the second mistake is the multiple comparison test selection. So this article concludes that the classic ANOVA test should be performed when the data is homogeneous, normal, and balanced or unbalanced, and the Wilks ANOVA test is to be performed when the data is heterogeneous, normal, and balanced or unbalanced. Regarding the selection of multiple comparison test, each multiple comparison test is appropriate for some situations, and the standard of choice is the ability to control type 1 error and the degree of power detecting the significant differences between groups. Applied to Bai and Costin, ANOVA outperforms logistic regression for the analysis of check all that applies data. In this abstract, Bai and Costin suggest the use of logistic regression for the analysis of check all that applies kata data. At the same time, based on theoretical considerations, they criticize the use of ANOVA for such data. They show that logistic regression is flawed due to an inflated type 1 error rate relative to the nominal level, and it is therefore not reliable to use this model for inference on check all all that applies data. At the same time, the results confirm the applicability of ANOVA based in statistical inference. Multiple choice questions. Question number 1. A researcher employs 4 different weaning foods for the treatment of children under 5 years of age diagnosed with uncomplicated severe acute malnutrition and assesses the corresponding changes in weight after a period of 8 years. A total of 20 children are divided into 4 groups with 5 children each, and the change in each child's weight is recorded. At alpha equal to 0.05, the hypothesis that there's no difference among the weight can be rejected if F value is equal to critical value, B, F value is less than critical value, C, F value is greater than critical value, D, F value is less than P value, and E, F value is more than P value.
C.
Beta.
C.
C. Yes,
C.
yes, yes, the answer is C. The hemoglobin levels of 3 groups of pregnant females are given as group 1, group 2, and group 3. The calculated F value comes out as 13.5 and the critical value is 3.32. In process of testing the hypothesis, one of the statements most accurately describing the calculation is A, all 3 samples are from the same population. B, group 1 and group 2 samples are from the same population. C, group 1 and group 3 samples are from the same population. D, at least 2 samples are from the same population, and E, at least 2 samples are from different populations.
E. D.
E.
D.
D. Yes, the answer is E. Demonstrate the effect of smoking on the birth rate of newborn babies. A study divided pregnant women in the area into active smokers, passive smokers, and non-smokers. The sample mean birth rates, when plotted on a graph, give high variability between the 3 groups. The distribution of the group means can most likely be A, cluster more tightly than within group, B, spread out more than within group, distance is small relative to random error, distance is equal relative to random error, and the spread is less within the group.
C.
C.
No, the answer is B. B. Yes, the answer is B. In a study, subjects are randomly assigned to one of the 3 groups, control, experimental A, or experimental B, for the treatment of hypertension. After treatment, the mean scores for the 3 groups are compared. One of the following used within the F ratio as a measurement of the variance of individual variations is A, sum of squared error, B, mean squared error, C, sum of squared treatment, D, mean squared treatment, and E, grand mean.
Beta.
B.
B. B.
It is A, sum of squared error. To determine whether the statistic test of ANOVA is statistically significant, it can be compared to a critical value. The 2 pieces of information most needed to determine the critical value are A, mean and standard deviation, B, mean squared error, mean squared treatment, C, sum squared error, sum squared treatment, D, expected frequency and obtained frequency, and E, sample size and number of groups.
C. E. C.
No, the answer is E, sample size and number of groups. Assuming no bias, the total variation in a response variable is due to error, unexplained variation, plus differences due to treatment, which is the known variation. Suppose the critical region for a certain null hypothesis test is of the form F is greater than 9.48 and the computed value of F from the data is 1.86, then null hypothesis should be rejected. B, null hypothesis should be accepted. C, the level of significance is given by the area to the left of 9.48. The level of significance is given by the area to the right of 9.48. And the hypothesis is signified as two-tailed.
Alpha.
D.
H note should be rejected.
Alpha. No, the answer is D. The level of significance is given by the area to the right of the F value. The results of a clinical trial to test the effectiveness of a sleep-inducing drug are compared. Assuming that the null hypothesis being tested by ANOVA is false, the probability of obtaining an F ratio that exceeds the value reported in the F table as the 95th percentile is A equal to 0.05, B less than 0.05, C equal to 0.5, D less than 0.5, and E equal to 1.
B.
Alpha.
Beta.
Alpha.
Yes, the answer is B. Sorry. Yes, the answer is B. ANOVA results do not identify which particular differences between pairs of means are significant. The most important function of a post hoc analysis of ANOVA is A. Controlling type 1 error, B. Controlling type 2 error, C. Controlling sum squared error, D. Controlling some mean squared error, and E. Controlling degrees of freedom.
Alpha.
C.
Alpha. D.
Alpha.
C.
Alpha.
Yes. If a multiple t-test is performed instead of using an ANOVA to compare 10 groups, one of the following most likely to occur is A. There is no difference between using an ANOVA and using a t-test. B. Nothing except that making multiple comparisons with a t-test requires more computation than doing a single ANOVA. C. Making multiple comparison with a t-test increases the probability of making a type 1 error. D. Difficulty to determine if any statistically significant group differences have occurred. And E. Problem to set the critical value for F.
Beta.
D.
Beta. B.
D.
No, the answer is C. The answer is C. Making multiple comparisons with a t-test increases the probability of making a type 1 error. A researcher randomly assigns 30 college students into 3 equal study groups, early morning, afternoon, and late night, to determine if the period of the day at which people study has an effect on their attention. On the 7th day, when an ANOVA table is computed, it is noted that the mean square within groups is larger than the mean square between groups. The results indicate A. High F value, B. Same F value, C. Low F value, D. Gradually increasing F value, and E. Gradually decreasing F value.
C.
Alpha.
Low.
C.
D.
Yes.
Alpha.
The answer is C. Low F value. This is the key of the MCQs, and please like and subscribe our YouTube channel. Thank you very much.
Thank you very much, Dr. Ramsha. Very nice presentation, especially one of the MCQ. I must appreciate it. I was thinking of having a comment about it, but I'm really satisfied that you have already picked that point and presented in the form of MCQ to emphasize it, reiterate it, and to give highlights to it. That why we are using t-test, why we are using ANOVA tests, and why we are having different groups if there are two groups, and why we are having t-test when we have more than two groups, why we have ANOVA test, and why not we just do the t-test analysis again if we have two groups, and then we can compare the value for the significance with the third group and with the fourth group. So the most important point that have been highlighted and already mentioned is that the type 1 error would increase if we start having comparisons among the group that are more than two in number. We have already talked about the t-test, that first we have to see the variance, we have to see the standard deviation, we have to calculate the means, and then we have to compare the means. In ANOVA, again, we are comparing the means. We again have to calculate the variance and the standard deviation from the mean of, and then with another important thing is ANOVA can only be applied if the data is continuous, if the data is normally distributed. If these assumptions failed, now my question is from the class, if anybody wants to answer it, if the assumptions fail that the data is categorical, it is present in normal distribution, but it is not continuous, the variance is known. So how would you go about it? Would you still want to apply ANOVA test or something else?
No, madam. If the data is not normally distributed, then we go to non-parametric test. There is
Non-parametric test, yes.
every test has its counterpart. T-test, ANOVA test. These are really Cox and rank sum test, and Kruskal Wallis test. Various tests available. But if the
Right.
sample size is larger than 30, then central limit theorem allow us that if the normality is violated, because when the sample size is more than 30, the central limit theorem described that the data become normally distributed, and the
Right.
sample
So we
mean
can have certain tests.
equal
Now, the
to
next part of
population
my
mean.
question is, Khansa, I agree that if the distribution is not normal, but still the sample size is large enough, then we can apply the normal distribution theorem, the center limit theorem. both says one thing, that when we have multiple means, then the chances of the mean of the sample to lie on the actual mean of the population, that increases. So we are playing on this chance. My next question is that as we know that there are one sample t-test and we have its version for non-parametric test. We have paired sample t-test or dependent sample t-test, and we have the version in Mann-Whitney non-parametric test. Similarly, we have independent sample t-test and we have Kruskal-Wallis test. What is the test that has to be applied on more than three groups? Or three groups or more than three groups, if the variables are categorical, they are not continuous. What is the name of that test?
मैडम chi-square अप्लाई कर सकती हैं अगर इंडिपेंडेंट वेरिएबल्स की जो है वो कैटेगरीज 2 से मोर हों.
Okay, one can be the chi-square test, but any better test that can be applied if we have the data that is categorical?
मैडम रिग्रेशन अगर हम अप्लाई कर सकते हैं अगर कैटेगोरिकल जो है वो उसकी इंडिपेंडेंट वेरिएबल्स जो है वो कैटेगोरिकल हो, लेकिन उसमें आपकी भी
Which type of
डिपेंडेंट
regression analysis?
मैडम ये डिपेंड करता है कि अगर आपका आउटकम है